Okay, in the last lecture we revisited the XOR problem that used Gaussian units, wherein the input space was transformed non-linearly and then we were able to separate the points in the feature space through a perceptron. Now, there is this motivation of having these Gaussian units as a basis where we can solve the interpolation problem in the multidimensional setting, and we will visit this problem here. So, the problem statement is as follows: given a set of n different points xi belonging to R m naught. So, you can call whichever dimension you want, here I have used m naught, and we have n such points I equals 1 so on till n, and a corresponding set of n real numbers d sub I, they are all scalars. We would be interested in finding a function from Rn to R such that capital F acting on this data point xi gives us the scalar d sub I for all these n points. Now, as I mentioned, we would like to use these radial basis functions that we have used earlier while solving the XOR problem. Now, this function capital F acting on this data point x can be written in this form. It is a linear combination of these non-linear functions phi acting on the data point. We assume that these non-linear functions are smooth, and we look at the Euclidean norm between the data point and some chosen centers xi, and that is how we set this problem up, and we have a linear combination of these, and our interest is to solve for the weights whose coordinates are wi, I equals 1 to n. And you may wonder at this stage why we are bringing in this L2 norm here within this non-linear function. L2 norm has radial symmetry, it is isotropic, and so it does not skew the direction, and we want to have these basis functions, these non-linear basis functions, and we want to have them with radial symmetry. So, therefore, we want to call them as radial basis functions. The Gaussian is an example of the radial basis function. Now, phi j comma I is given by phi of xj minus xi. So, I fix the centers, I fix these xi's first. If you look at it, you look at this expression, it is phi of x minus xi, and x can vary by selecting the points xj for j equals 1 to n, right. So, I goes from 1 to n and j also goes from 1 to n, and we have the desired vector which is d1 to d suffix n. So, these are scalars stacked to form this vector, and we have the linear weight. Now, this is a pretty straightforward problem if we express this in the form of a matrix. Now, I have phi 1 1, phi 1 2, phi 1 3 so on till phi 1 n, and I have these w1, w2, w3 so on till wn. So, if you look at this matrix and individually each row corresponds to an equation, right. D suffix 1, d1 is phi 1 1 w1 plus phi 1 2 w2 so on plus phi 1 n wn so on and so forth for all the points 1 to capital N. right. So, we form a matrix which is this big phi comprising of elements phi j I, j and I go from 1 to n. So, we have this matrix equation which is phi times this weight vector W equals the desired vector D, which is straightforward. W is phi inverse T, right. This is straightforward solution. Now, you may wonder about the existence of this inverse. Why this is crucial? This is crucial because phi depends upon the choice of the nonlinear function phi that you started off with in the first place, and you populated the entries in this matrix phi using that nonlinear function by evaluating at different data points, and if this has to be invertible, then the original nonlinear function should have certain properties that makes this work out. Fortunately, we have a theorem from Micheli that states as follows: let xi I equals 1 to n be a set of distinct points in Rm0, then the n by n interpolation matrix phi whose jith entry is phi ji given by this quantity is non-singular, and plenty of such functions exist, and this is very important because it gives us the freedom of choosing the basis than restrict ourselves with a particular function. So, there are many examples. I will state 2-3 of them here. The first is this multi-quadrics, where phi of r is given by square root of r square plus c square. This is just the length in L2. C is greater than 0 and r is a real number. We have inverse multi-quadrics, which is just the reciprocal of the multi-quadrics, and we also have these Gaussian functions that we are familiar with in this form. So, one thing you will have to pay slight attention to, do not confuse this Gaussian function with the Gaussian distribution. I have not given a normalization factor. I mean, when you think about the Gaussian, people have a tendency to put this constant and then get this 1 over root of 2 pi sigma square and then do these things. So, this is general form from an exponential family and we treat it like this. These functions, the inverse multi-quadrics and Gaussians, are localized, that is phi of r tends to 0 as r tends to infinity. That means, if you choose your radius to be very large, the function becomes localized or it shrinks to 0, and this has an interesting consequence. This has an interesting consequence in learning. Sometimes when we have to deal with the neighborhood radius, for example, in the self organizing map we choose again these Gaussian units, and when we have to fine tune the map, the radius actually it shrinks to 0 and it becomes sort of. So, there is this duality between when r equals 0 and r equals infinity, and this behavior is important for us, and when r goes to infinity it really becomes localized. And the multi-quadrics is unbounded, and as r goes to infinity this heads to infinity. So, therefore, we will have to take care to put bounds if we were to use this function within our interpolation problem. Okay. So, with this we complete the interpolation problem, and this is very important because we will revisit this problem in the context of the RBF network, the radial basis function network. At the output layer of the RBF network, we will have to solve this particular problem where we have to solve for the weights or the synaptic weights that connect the hidden units with the output layer, right. In that context we will revisit this problem, and we will stop here.